Welcome to this explainer. Today, we're conducting an inductive case study analysis examining the intersection of artificial intelligence, cognitive development, and modern pedagogical structures. We're examining a specific, real-world primary account that encapsulates a paradigm shift occurring in our educational landscapes. By analyzing this single event, we extract profound insights in how advanced technology is reshaping learning, and crucially, how our institutions struggle to adapt to these new cognitive realities. First, we have to recognize the fundamental thesis here, the structural friction between digitally native students and historically anachronistic educational institutions. We are witnessing a rapidly growing disparity. On one end of the spectrum, we have dynamic, AI-assisted problem-solving methodologies yielding almost instantaneous results. On the other end, traditional pedagogical models built on strictly linear, sequential learning. The core tension lies precisely in this divergence. Our educational frameworks were designed for an era devoid of these algorithmic tools, creating a profound dissonance for students who utilize them natively. So let's look at the context. Our empirical observation originates from a specific technological interaction documented within an educational program known as the Eureka course, located in Maana. We're observing an educator and a highly gifted student enrolled in this course. It's essential to contextualize this setting. We are analyzing an environment dedicated specifically to technological and programming education. This makes the subsequent events and the educator's reaction to them particularly significant. It provides us with a controlled microcosm to observe the collision between traditional adult instruction and modern digitally native intuition. The catalyst for this observation was a spatial coding anomaly. Specifically, the educator was attempting to program a virtual mechanism, a touch-activated wing door designed to open along the z-axis. However, a failure occurred in executing the program. The code simply would not function as intended. Now, this failure represents a standard computational roadblock. In a traditional learning environment, overcoming this spatial programming hurdle would typically necessitate a protracted process of manual debugging, perhaps consulting static reference materials, or engaging in sequential trial and error. Faced with this programming dilemma, the educator initiated a reversal of the traditional pedagogical hierarchy by seeking the assistance of the gifted student. Upon being presented with the non-functioning code, the student immediately initiated a highly efficient, autonomous technological intervention. Notice that there was no hesitation. There was no reliance on standard textbooks and absolutely no linear debugging process. Instead, the student instinctively pivoted to external artificial intelligence to facilitate a resolution. This immediate pivot is an absolutely critical data point in understanding modern cognitive problem-solving workflows. The students' rapid problem-solving methodology utilized four distinct, highly sophisticated stages. First, they uploaded the faulty parameters directly to the Claude large language model. Second, the student engaged in prompt engineering, asking how to modify the code to achieve the desired outcome, typing the parameters in fluent English. The educator specifically noted that the student executed this freely as a native, utilizing it as a mother tongue. Third, upon receiving the generated responses, the student empirically tested the output within the Eureka environment. Finally, within mere minutes, the optimized and functional code was transmitted back to the educator via WhatsApp for immediate implementation. This sequence represents a complete, self-contained cycle of analysis, delegation, verification, and deployment. This seamless interaction prompted a profound comparative analysis from the educator, who documented feeling in true awe. The educator explicitly categorized the adult generation as mere immigrants to the world of programming and computers. The imagery utilized here, of adults left astounded and panting at the rear gate, brilliantly illustrates the stark cognitive and operational disparity at play. It is a highly candid admission from an instructional authority that the technological fluency of the student has fundamentally outpaced the traditional framework of the instructor. The crucial point we must distill here is the distinct operational divide. On one side, we have the digital immigrants, whose problem-solving paradigms remain constrained by traditional coding methodologies and sequential logic. Contrasted directly against this are the digital natives. For these students, interacting with artificial intelligence is not an external or novel process. It functions as a primary native cognitive extension. Their ability to formulate complex prompts with mother tongue fluency demonstrates a symbiotic relationship with machine intelligence. It's a relationship the previous generation struggles to comprehend, let alone replicate at the same velocity. Transitioning from this micro-level observation to macro-level implications, we must critically evaluate the utility of our current institutional frameworks. The source text explicitly forces a systemic pedagogical critique. When a student possesses the capability to independently synthesize solutions using advanced neural networks in a matter of minutes, the structural validity of the standard classroom is fundamentally called into question. We are observing the glaring anachronism of modern schooling, a system that remains largely tethered to a pre-digital philosophy of knowledge acquisition and retention. Let's examine the core components of this paradigm shift. First, we see the autonomous integration of external AI tools. The student required no instruction whatsoever to leverage Claude. Second, we witness the rapid execution of complex spatial problem solving. And third, these capabilities expose profound friction with linear traditional learning environments. Standardized curricula frequently fail to harness or even acknowledge these advanced competencies. Instead of fostering this highly efficient prompt engineering and systemic troubleshooting, traditional environments often force students to power down their most effective cognitive extensions the moment they enter the classroom. Ultimately, this single observation demands that we confront a foundational, provocative inquiry regarding educational reform. As the educator in our source material asked with profound clarity, what is a child of this caliber doing in a school from the century before last? How can institutions designed for an industrial compartmentalized era adequately serve the cognitive realities of today's hyper-integrated, AI-fluent student? We must ask ourselves, are our educational structures prepared to evolve? Or will they remain panting at the rear gate, fundamentally disconnected from the brilliant realities of their own students? It is a question our institutions can no longer afford to ignore. Thank you for joining me for this explainer,